So reduction oxidation reactions, or redox for short, is basically following the movement of electrons from here to there, from basically chemical A to chemical B. Right, so today I'm just going to be going over a really brief kind of recap of the fundamentals of redox. There will be a couple more videos probably on redox. So first of all, what is reduction? I'm going to say is red. And what is oxidation? Well, reduction is the gain of an electron. Gain of an electron. And oxidation is the loss of an electron, right? And so this right now, it might sound a little weird, but I promise you it's not going to be that hard. It might be a little hard to remember exactly which is which and what is what. So a mnemonic that I've come up with, or no, I've definitely not come up with this, but the mnemonic that I use is Leo the lion goes grr, right? And basically that'll stand for lose electron, oxidation, gain, I'm going to put E minus for electron, is reduction, right? Another mnemonic that I find is commonly used if you hate the environment is oil rig, right? Oxidation is losing, reduction is gaining, right? But that's if you are a staunch hater of Earth, and I don't think any of us are, right? But I mean, ultimately, in the end, it's whichever one works better for you. I'll be using Leo the lion goes grr. Okay, so what's the point of learning about redox equations, about anything like that? Well, basically, it's because redox, right? In moving the electrons around, right, we can get energy going. Think, for example, in the mitochondria, right? This is my mitochondria. Might be a red blood cell. In my mitochondria, right, we're gonna basically have some redox equations, right? NADH plus H plus becomes NADH, right? So, or sometimes, we can also use it to extract metals from ore. Basically, redox is necessary for life. So let's learn a little bit more about it. So say we have the reaction zinc metals plus copper sulfate becomes zinc sulfate plus copper. Right, and this is copper 2 sulfate and zinc 2 sulfate. Okay. So what is being reduced? Red. And what is being oxidized? Ox. Okay, well, it might look like really confusing and you might be like, what? I have no clue what to even think about. But like all things chemistry, there's always a bunch of rules that you can memorize to help you out with this sort of thing. So let's go over those rules. What we're going to do is we're going to assign each element. It might be helpful if I do it here. We're going to assign each element what's called an oxidation number. Not each, basically every single element, right? So SO4 is going to have to be split up into S's and O's. Okay. So what is an oxidation number? Oxidation number. I'm going to abbreviate number to be just, a hashtag. It's basically a bookkeeping method that scientists have made up. That doesn't seem spelled right. That's because it needs a hyphen. Bookkeeping method that scientists have made up. Basically, it's super arbitrary. It's just literally just scientists have made it up, right? It's a helpful bookkeeping method, but it's super arbitrary. It's not anything to do really with any other parts of chemistry, right? So there are a couple rules to know. So let's go over it. So assigning oxidation numbers, right? So the oxidation number of a free element is always 0. Ox number of free element equals 0. So, this might be confusing, but like H2 will have an oxidation of 0. Zinc will have an oxidation number of 0, right? So that's good to keep in mind. Another one, the oxidation number of a monoatomic is equal to the charge of the ion. I should have actually, let me append that, monatomic ion, charge of ion. So this might be confusing. So think like Cl minus is going to have an oxidation number of number 1, or H plus is going to have an oxidation number of +1. Okay, so far so good. Next, we have the oxidation number, ox number of group 1A, group 1A. So these are all the alkali metals, have an oxidation number of +1. So think Na has +1. Right, another thing to note, oxidation number of group 2A, right? Remember, because group 2 and group 1A are almost always, lumped together. Group 2A, these are the alkaline earth metals, right? That's always equal to +2, right? So like calcium is +2. Okay. And then these are like pretty easy, right? We have another really easy one, the oxidation number of group 7A, right? So these are going to be all of the halogens, right? Are going to be almost always -1, unless, so actually let me just finish this guy, like earlier, like Cl minus is going to be -1, unless in the presence of a more, so I'm going to put 2 less than signs because it's going to be group 7, so halogen H is less than in terms of electronegativity of a different element, diff element, right? So what does that mean? Basically, I'll give you an example for this one because this is just easier to kind of exemplify, right? In HCl, the chlorine will have a -1 oxidation number, and that makes sense, right? Group 7A, it's a halogen, it's always going to be that. However, in HOCl, the O is more electronegative than the Cl. Therefore, this is going to be +2 or +1. This is going to be -2, and then that means that Cl is going to be +1, right? Notice how when it's alone, it conforms to the rule that group 7A is always -1. In the presence of a more electronegative element like oxygen, we're going to be +1, right? So it can change. Moving on, we have that the oxidation number, let me just clean that up for you. The oxidation number of oxygen is usually -2, unless it's a peroxide, right? Peroxide, in which it's a -1, or once more, if it's more electronegative, then it can change. So O less than electronegative, right? So once again, let me just help you out with this guy. So like it's like OF, right? Fluorine is more electronegative than oxygen. Remember our periodic trends, right? So oxygen is going to be +2 instead because it's -1. F is -1, right? And then peroxide, right? H2O2. Each oxygen is going to be -1, -1. Each H is going to be +1. Okay. And final rule should be that the sum of all charges, or sum of all oxidation numbers in a compound, will equal its charge. So what does that mean? That sounds really confusing, but hear me out. Carbonate, CO3, has a charge of 2-. We know from our previous oxidation rules that oxygen, because there's no more electronegative element, nor is it a peroxide, we know that we're going to have that oxygen's oxidation number is -2. Okay, then let's figure out carbon's oxidation number. Well, we can do some simple math and assign X for carbon. Then we know that X plus 3 times -2 is going to be equal to -2. Solve that out, we figure out that X equals 4. Right, so carbon's oxidation number is going to be positive 4. Okay, so here are all of your here are all of the rules right there that you're going to have to know. Yeah, isn't chemistry so fun? Okay, let's trust me, it's a lot easier than you think. You don't have to really remember too many of them. So let's look at this problem again. So what's being reduced? What's being oxidized? Okay, well, first off, remember we have to assign our oxidation numbers. So zinc is a free element, so we're gonna have 0. Oh, I like to write my oxidation numbers directly above the element. Yeah, I find it easier. You can do them however you want though. And then copper sulfate. Okay, that looks confusing, but we know that sulfate is a polyatomic, right? So sulfate, SO4, what is that? It's a 2-. We also know that O is probably always going to be a -2, and we know this is true because sulfur is not more electronegative than oxygen is, right? Okay, so we set up our math equation again. X is the oxidation number of sulfur. Plus 4 times -2 equals -2. X equals 6. Okay, so then we have 6 above our sulfur. And then copper. Well, this looks confusing, right? Wait, it's not a polyatomic. However, we know that it's a compound, right? CuSO4. And we know that its total charge is going to be 0. Therefore, we know that Cu's charge must equal SO4's charge. And we remember from our very last, remember from this guy that the sum of all oxidation numbers in the compound is equal to its charge. Therefore, copper's oxidation number must be +2. So far on this side, we have 0, +2, +6, and -2. Okay, I really would like you to give the other side a try. Just try it. You don't have to get it right. I will come back. We'll come back and we'll do it together. So pause the video now and give it a try. Did you try it? I hope you did. Okay, so let's figure out the other side. Okay, well, copper is easy. Copper is 0, right? And then next is zinc. Zinc is going to be +2, right? And then S is still 6. O is still -2. Okay, so now what do we notice? We notice that we have zinc right here, changing numbers. And we also notice that copper right here is also changing numbers. I'm gonna try to color code it. So the pink highlight is gonna be red and the blue highlight is gonna be blue. Okay, so let's look at zinc. What is zinc doing? Zinc is going from 0 to +2. Okay. And we know that copper, Cu, is going from +2 to 0. Okay, now we got to figure out what's being reduced, what's being oxidized. Seems really hard, it's surprisingly simple. So we remember our mnemonic Leo-Ger, or if you hate the environment, oil rig, and whatever you want, I guess. My way's the best way, probably. But yeah, no, it's just whatever is nice. Losing electrons is oxidation. Losing electrons is oxidation. Okay, so what should be happening? Theoretically, then, what we should be finding is that losing electrons would mean that we would think that it's getting more negative, but it's actually getting more positive, right? Because we know that electrons are minus charge. Therefore, if we're losing electrons, we should be getting more positive. And gain electrons is reduction. Gaining electrons, we would think about it as getting more positive, but it should actually be getting more negative. Okay. So what's happening? Zinc is becoming from 0 to +2. It's getting more positive, right? So zinc is being oxidized. So let's write that down here. Zinc to zinc SO4. And then copper is going from +2 to 0. It's getting more negative. Therefore, it's being reduced. Therefore, copper is being reduced. Right? That was that was shockingly simple, right? That was really easy. Okay, just one thing to really quickly note is that when we're looking at zinc and copper right here, sometimes questions will ask, what is the reducing agent? Reducing agent or the oxidizing agent? Oxidizing. Sorry, I was suffering from mental deficiency. Okay, so oxidizing agent, right? Okay, so what is it? We can't really say that the thing that's being reduced is the reducing agent, right? Because that wouldn't make any sense. However, the thing that's being reduced is causing the element that's being reduced, in this case copper, is causing, the element that's being reduced, copper, is causing the zinc to become oxidized, right? So copper is our oxidizing agent, and conversely, the thing that's being oxidized, zinc, is causing the copper to be reduced. Therefore, we can say that our zinc is the reducing agent, right? So I guess if you wanted to, you could append or amend our mnemonics to be Leora / Garoa. But I just think that's kind of dumb. Just kind of like, if you look at it, you can kind of figure it out, right? But if you really need a mnemonic, boom, right here is your ultimate mnemonic. It's a little weird, but just whatever floats your boat. Okay, so I mean, that's pretty simple. That's pretty easy, right? So let's do a couple of practices, right? And remember, don't feel bad if you have to either write down these rules or if you have to kind of remember them, because these are so important that you do know these. Okay, let's do a couple of questions. Consider this reaction. Sorry, let me zoom back in. Consider this reaction MnO4 minus plus I minus. MnO4 minus plus I minus becomes Mn plus 2 plus I2. Of course, it's going to be in the presence of a hydrogen, right? And let's figure out what's being reduced, what's being oxidized. So reduced and oxidized. I shouldn't have spelled these out. Okay, well, remember, whenever we have to figure that out, we do have to figure out what our oxidation numbers are. Okay, oxidation numbers. O is always going to be -2. I is a monoatomic ion, so we know that it's going to be equal to its charge. And then let's go to the other side, right? I is by itself 0, monatomic ion plus 2. Okay, now we just have to figure out this side's manganese's charge. And if we do that, it's going to be that X plus 4 times -2 equals -1. And we're going to have that manganese is going to be +7. Okay, now let's consider what's changing. Oxygen is gone, so we just completely disregard it. That means that we have this manganese, and then we have this iodine. Okay, manganese is going from +7 to +2. It's getting more negative, right? And we refer back to Leo, the lion goes grr. Right? More negative. Okay, what is more negative? More negative, it's losing an electron. No, it's gaining an electron. Sorry, I completely fell for my own thing. Yeah, it's gaining an electron, right? So it's being reduced. So MnO4 to Mn plus 2. Mn. Right? And what's being oxidized? Well, the opposite, right? The only other thing that's changing. I minus to I2. Okay. Not that bad, not that hard, right? So, and if we were to be told what's the reducing agent, Ra, what's the oxidizing agent, Oa, then we'd be able to say that the thing being reduced is the oxidizing agent, and the thing being oxidized is the reducing agent. Okay, good luck. Thank you so much.